thank the organizers for inviting me to give this talk. As we've seen, a lot of turbulence is connected with simulations, and you can get a lot of the physics from simulations. But I'd like to point out that, in fact, we can get some analytic information about, in our case, the Enstrophy cascade in 2D quantum turbulence. And this allows some unique insights, I think, into the physics of what's going on. And in fact, I'd like to say that there's really a correspondence between the 2D classical turbulence cascade and the 2D quantum turbulence cascade. And in fact, I think the quantum case can profitably show some aspects of the classical case. So let me outline. I'd just like to briefly review the two-dimensional Kosterlitz-Thales renormalization. I'll then talk about the vortex dynamics in a temperature quench, which is a phase ordering transition. We started at high temperature with a lot of vortices. We suddenly quench to low temperature and ask, how did the vortices disappear? And as I'll show, that's connected to this Enstrophy cascade. I'll then talk about how we can formulate this Enstrophy cascade from large to small scales. It's a forward cascade. We can also study the dynamics of the cascade, and then I will compare to a recent simulation by a group in New Zealand which showed the existence of the Enstrophy cascade. We actually proposed our model many, many years ago. It attracted zero notice, as far as I can tell, because this group did not even reference our early work. I still don't understand quite why not. Okay, well, these two folks became quite famous in 2016 for winning the Nobel Prize. They were among the first to realize that the lowest energy excitations in superfluid helium films are these plus-minus vortex lines. These are topological objects connected by a circular loop. These are dipoles, and of course the energy reduction comes because you cancel the flow field at large distances, so that the energy of the loop divided by kT goes logarithmically in the separation of the vortices. It's proportional to the thickness of the film. I'm going to write all of this stuff out in front as a factor K, capital K, which is a dimensionless form of the superfluid density. It's basically the areal superfluid density divided by the temperature, and then these universal constants out in front. Now, these vortex pairs can kill superfluidity. In a flow field, if you apply a flow field, those dipoles will orient to try to oppose the applied flow so that their backflow opposes any applied flow. What that means is that rho s can be driven to zero if you have enough of these vortex pairs of large enough separation that can identically drive rho s to zero. And of course, that's what happens. There's two key ideas in the theory. First of all, that to get the superfluid density, you simply add up the polarization currents from all of the pairs. So it's basically, there's a starting superfluid density from excitations other than vortices, but then you have the contribution from the vortices, the polarizability of the vortices, and the probability of finding a pair of separation R. And I'll use later in the talk this distribution function, which is basically the number of vortex pairs per unit area of separation between R and R plus dr. In this thermodynamic case, in the equilibrium, that's just the Boltzmann factor. But this is a screened energy, and so you really need an equation for this screening due to the fact that if you have a large pair, there's a bunch of smaller pairs in between. The flow field of that large pair polarizes the smaller vortices, lowers the energy needed to create that large pair. So you have a screened energy, it's the bare energy divided by the dielectric constant, then gives you this renormalized energy of a pair. These are now two coupled integral equations for the macroscopic superfluid density if you iterate as a function of separation out to infinite separation. More usually, you convert those integral equations to differential equations, shown here. This is still in units with respect to the separation of the vortices. And this parameter y is basically proportional to that distribution function. And you'll notice this equation has an instability when k approaches the critical value of 2 over pi. It changes sign. And what that means is that if you're at low temperature, where k is less than 2 over pi, this is a negative number, so y is driven to 0, but that means k becomes a constant. That means you have a superfluid state. However, as you raise the temperature, you will finally get to a point where k is less than this 2 over pi. This then becomes a plus sign. Y is driven to infinity, and k is then driven to 0. And that's a normal fluid. And of course, in the Kosterlitz-Thalys case, this gives rise to a sudden jump in the superfluid density. And that's shown here. If you start with a given film thickness and raise the temperature, you hit this point where you get an abrupt sudden drop of the superfluid density to 0. And, well, they showed it obeys this universal value. Okay, well, now I'd like to turn to what seems like a separate question. What if we sit at the Kosterlitz-Thalys temperature, where we have a lot of thermally excited vortices, and we suddenly quench to a final temperature of 1/10 of TKT? Well, we know the vortices are going to disappear at low temperature, and the question is exactly how do they disappear? Well, we can use a Fokker-Planck equation for the vortex pair distribution function now as a function of time. And this is the equation that was worked out by these rather famous individuals. This is in dimensionless units. I'm taking t in units of the diffusion time, the diffusion constant over the square of the vortex core size, and r in units of the core size. This is basically a diffusion part of the equation, and this comes from the attractive interaction between the vortices. And I'll notice, because we have a finite diffusion time, we have friction on the vortex cores. The bigger tau 0 is, the bigger the friction in the problem. K here, again, is the superfluid density divided by the temperature. It's determined from one of those recursion relations, the Kosterlitz recursion relation. And in fact, in thermal equilibrium, when d gamma dt is 0, these are just those same two equations of Kosterlitz and Thalys, where in that case, gamma is simply the Boltzmann factor, but for a logarithmic interaction, that's simply a power law decay in the separation of the pairs. We can solve that Fokker-Planck equation. We actually found exact solutions. Involves the hypergeometric function, but it also then shows the time-dependent decay in terms of basically two different dynamic exponents. There's a dynamic exponent z, which in turn gives the dynamic length in this phase ordering problem. That gives a length which increases as t to the 1 over z. But then there's a second dynamic exponent, which we've called z scale. That's a dynamic exponent first seen by Minhagen in XY simulations. So we can then follow this decay. We do both numerical and analytic solutions. This is for a quench from 0.9 TKT to 0.1 TKT. The power law, it falls off, is then T to the 1.56. This Z scale depends on the initial temperature. If you start directly from the Kosterlitz-Thales transition, you find a 1 over T variation, but as you quench from, say, 0.8 TKT, it's nearly 1 over T squared. We can also follow the superfluid density scales back to 0, back to 1 with time. If you're worried that these, we're solving this Fokker-Planck equation, you might think, well, maybe there's something wrong with that equation. In fact, we did finite time quenches. Here's that instantaneous quench curve that I just showed you. If we now simply quench much slower, linear quench over 100 diffusion times, what we see is the vortex density stays high, and then only finally at very long times rejoins the rapid quench case. This was also studied in the XY model by Cugliandolo. Here's her instantaneous quench, and then at finite times she sees just the same behavior that we found. So we think this equation really is a description of the system. I'll point out, this is the exact opposite of the Kibble-Zurek prediction. Kibble-Zurek is completely wrong for the case of superfluid helium because there are vortices above TC and below TC. I believe Kibble-Zurek is only correct when you don't have any topological structures above TC and the topological structures only appear below TC. And it's not the case in superfluid helium. I've tried to argue with Zurek. He's impossible to argue with if you've ever encountered him. We can also get the distribution function as a function of time. Okay, we said in thermal equilibrium, it's simply a power law fall off. As we now start to quench from 0.9 TKT to 1/10 of TKT, of course, it's the smallest vortices that leave first. They leave by annihilation. But as time goes on, we start to see the larger vortices also start to decay. And in fact, you see this increasing flat distribution function. This is a phase ordering process. This length here, this increasing length size, is just the dynamic length, the dynamic correlation length of the system. We can identify that this is now the correlation length given by this dynamic exponent. And what I'll point out, this, in fact, is a turbulent Enstrophy cascade. The phase ordering in this problem occurs via the Enstrophy cascade. We have a constant flux of vortices from large scale to small scales over this increasing scale size. Yeah. It's the distribution function, the number of pairs at a given separation. So, versus the separation of the pair. Yes. Exactly. The second term is due to the attractive interaction. The dissipation is from the diffusion term. Yeah, I'll come back to that equation, in fact. Our initial, we took the Fokker-Planck equation and did numerical solutions and published those in 2001. We realized later that we could get exact solutions of that Fokker-Planck equation. Yeah, yeah. I mean, and the numerical and exact solutions agree completely. Ah, okay. We are dealing with a system. We are dealing with a system coupled to a heat bath at positive temperature. So we don't allow any negative temperature states to form. That's why I'm only going to be talking about an entropy cascade. The energy cascade relies on negative temperature states. So, think of this substrate as being a thermal bath at a fixed temperature. Yeah. Yeah. Yeah, between R and R plus dr. Well, yeah, it's instantaneously going to zero. Yeah. Yeah, they're being pulled out by the thermal bath. Well, I mean, they're moving toward, R equal 1, A0, the core size. And at that point, they simply disappear from the system. They're pulled out. They annihilate. So if you call that 0, that's fine. But they're simply being pulled out at that point. Hmm? Yeah, we actually pull them out with a boundary condition. Exactly. Okay, so let me talk now about cascades. We've already seen one. Of course, in classical 2D turbulence, you have two cascades, an energy flux to large scales that goes as k to the minus 5/3. You also then have this Enstrophy cascade by Kreiknen, where you have a constant flux of entropy to small scales with a k to the minus 3 energy spectrum, plus some logarithmic corrections, which I'm not going to get into. Enstrophy is the square of the vorticity, the curl of the flow field. You take the square of that and integrate over the plane. That's the total entropy in the system. So the question is, what are the cascades in quantum turbulence? Well, people have found the inverse energy cascade in Ginzburg-Pidievsky simulations, k to the minus 5/3, and like sign clustering has been seen in BEC systems, and these are negative temperature states as Onsager predicted. We first proposed that you could have a forward entropy cascade in 2001. No one seemed to notice. It was finally in 2017 that a group in New Zealand published a simulation showing evidence of an entropy cascade in this case. And I'll compare with this simulation. So here's a simple cartoon of our cascade. It's a 2D incompressible superfluid film. We connect it to a heat bath at low temperature, a tenth of TKT. We inject pairs of large separation, capital R, at some rate q dot, so many pairs per unit area per unit time. So as we inject a large pair, they feel an attractive force, and because of the friction, they're able to move in that direction. And so they do. And let's see if I get another. Okay, here we go. Okay, so that first pair has now moved to a smaller separation, but we've now injected another pair, okay? And this continues. They keep moving to smaller and smaller scale. We keep injecting vortices of large scale, and finally they reach a point where they annihilate, and the energy gets pulled out by the thermal bath. this is a constant flux entropy cascade from this large initial scale to the small scale, the core size, where they annihilate. So again, we can use the Fokker-Planck equation, but we have to add in, for the turbulence case, a forcing function. This is a two-dimensional ring delta function. It injects pairs of this separation capital R at a rate alpha, which is just the q dot times tau 0 times the core size squared. And again, we determine the superfluid density from the Kosterlitz recursion. And again, in thermal equilibrium, gamma is just a power law in the separation. So we can solve this equation. For very small values of the injection rate, the solutions are very simple. Gamma is simply a constant proportional to the injection rate divided by the initial value of the superfluid density over temperature. And that's shown here for a very small injection rate. Now, that's for scales smaller than the injection size. There's actually a solution above that injection size. Some of the pairs that we put in get a little thermal kick to larger separation, but that falls off then very rapidly by a Boltzmann factor. And I should say, at these low injection rates, there's no change in the superfluid density. However, as you start to increase alpha, you get to a point where you get close to the thermal distribution of vortices at TKT. At that point, you can drive the superfluid density to 0. At e to the minus 7, it's driven rapidly to 0. In that case, the solution goes from a constant value to the point where it drops to 0. It then goes as a logarithmic factor, a logarithmic increase, up to the injection range, and then it becomes constant after that. These are basically the free pairs of the Kosterlitz-Thalès theory. Yes. It's the diffusion constant in our problem. It's already the frictional force is that diffusion constant, which is we've modeled it as the diffusion time. And I agree that the New Zealand simulations I'll talk about did put in dissipation into the Gross-Pidievsky. Vortex pairs. It's a way to do it. The cost of that Fokker-Planck equation is vortex pairs. We ignore the plus-plus correlation. It's a very short-range correlation, whereas the plus-minus correlation is quite long. That gamma is the two-point correlation function for opposite sign vortex pairs. The plus-plus correlation is very short range, and you can simply ignore it. Okay, I'm not clear on, I know the New Zealand simulation did add friction. let me point out, you can get in these solutions. This is now a solution with a much larger injection rate, and now even at 10 to the minus 12 injection rate, you can drive the superfluid density to 0. But let me point out the flux given by this, the flux of this Fokker-Planck equation, is simply equal to a constant. You can plug in these solutions. You find that the flux is constant over this entire injection range. So we can get the energy spectrum defined as in usual turbulence case. I'm now going to actually go back to dimensional units because you worry about the dimensions in turbulence. The total entropy is the kappa here is the quantum of circulation, so it's kappa squared times the density of pairs, which is an integral over the distribution function. And you can show the injection rate is also going to go as kappa squared times the rate at which you inject them. When you take the k-space transform of this, that is then the Enstrophy injection rate, just goes as 1 over A0 squared. You can define the Enstrophy spectrum similar to how you define the energy spectrum. And you can show, and this was work of Novikov and Subota, this is the form that results for the Enstrophy spectrum. But once you know the Enstrophy spectrum, you immediately know the energy spectrum. You just divide by k squared. Gives you then a k to the minus 3 energy spectrum. Now, that function f in kind of, I went to a dimensionless variable here, is given by this. You still have to do this integral. If we take the solution of a constant, which was proportional to the injection rate, proportional to eta, and plug this into here, we get a final result for the energy spectrum going as k to the minus 3 times eta times tau 0 divided by the superfluid density over temperature, times this function f tilde, which is basically an oscillating function. This is, we've unphysically introduced this because we've taken a transform, k-space transform, over a finite range. And anytime you take the transform of a square wave, you get oscillations. So basically, we can ignore this function. What to concentrate on dimensionally is the k to the minus 3 spectrum. It's linearly dependent on the injection rate. This linear dependence differs from the classical case, which when is the injection rate to the 2/3 power. It's because tau 0 is a new dimensional parameter. It has to appear in the energy. And in fact, you can see why it has to be there. If you increase the friction, you increase tau 0, but that means the vortices move slower, so there's more vortices piling up in the cascade. That gives you a higher value for the energy. The same thing, the dependence on temperature. Remember, this is superfluid density divided by temperature. Well, that also affects how rapidly the vortices move down the cascade. From the Einstein relation, if you're at lower temperature, you have faster motion down the cascade. That then lowers the energy. So proportional to T, as you lower T, you get less energy. And that's exactly what you expect. So we have this time-dependent Fokker-Planck equation. We can study all of the dynamics of the cascade formation. Here's thermal equilibrium at T equal to 0. If I now inject at R equal to 400, initially we get just a spike of vortices of that separation. But then as time goes on, the vortices start to move to both lower and larger separation. Again, these are getting thermal kicks. These are now starting to feel the attraction and move to, the delay to get the slides on here. You now are starting to have at least a little bit of a current towards smaller separations. This is delaying. There we go. We're starting to actually form the cascade. We're getting more flux. We finally get to a point where they start to annihilate, okay? And we define that to be the eddy time, and in this case, starting from 400, it's about 410 diffusion times. And finally, if we, at 4,000 diffusion times, which is about something like 4 eddy times, we then get to the constant cascade with constant flux. Okay, so it takes about 4 eddy times from flipping the switch on to finally get to the fully developed Enstrophy cascade. We can look at the decay of this cascade. If we turn off the injection at t equal to 0, then of course the decay starts at the injection scale because we're now no longer injecting vortices at that scale. So you basically see a decay of the flux and overall a decay of the vorticity. I'll point out that these solutions are exactly the same as we found in the temperature quenches. It follows exactly the same Fokker-Planck equation. I guess I went back to this is now identical, and this is now an Enstrophy cascade, which is the phase ordering process in this phase ordering correlation. Now, we can also look at the dependence. What if we just put a spike in the initial distribution of vortices? So at t equals 0, we put in some vortices and then let them go. Well, this also decays, and finally, after an eddy time, forms a constant value for gamma. That's this k to the minus 3 Enstrophy cascade. And that, again, starts to decay in just the manner seen for the temperature quench. Yeah, it's no problem. I mean, these are very tiny vortex densities. But I'll have to say, this is precisely the same behavior seen in the recent simulation in New Zealand. And I'd like to go into that simulation. It's a modified GP simulation. They do add friction, but the temperature is unknown. They don't particularly put a thermal bath, certainly, in contact. And they use very high densities of vortices. In our opinion, it's really not a superfluid. They have driven rho s to 0 by having such. But they start out with initial state. Basically, they're injecting pairs of large size. Think of a plus vortex in the middle here and a minus vortex in the middle there. That's a pair of large separation. And so this basically gives you a spike in the distribution of pairs. In their case, they show a spike in the energy spectrum, but it's the same thing. They then let this go, and you can see the pairs diffuse towards each other. It becomes less and less distinct where the pairs are. And finally, in this point, you have a full cascade of pairs of all separation. And they show that they go from this initial bump in the spectrum to a k to the minus 3 energy spectrum. So this is the Enstrophy cascade in this decaying turbulence. Their flux is, I wouldn't call that a constant flux, but it's probably close enough for jazz. And it takes about 4 eddy times to develop this full cascade, starting from this initial distribution. So it's exactly what we see in our simulations. It's GP add friction. Yeah, point vortex. Yeah, these are point vortices. It's hard to see. they put so many vortices in there, it's hard to tell. Yeah, I agree. I'll point out, you can actually get a distribution function of vortex pairs from these vortex maps. I'd really like to have this group go back to their data and see how the distribution function changes. I'll bet it would be very similar to what we've seen. So that's the reference if you... That's 1 over A0. They're just, it's a normalized, they're normalizing K by A0. No, it's the actual core size. It is the core, sorry, not 1 over, it is the core size in their simulation. Huh? You'd have to get it from the vortex densities. I don't know. I'll point out, you know, can we see this cascade in experiments? It's not clear. There have been now some BEC experiments where you can identify both plus and minus vortices. This is a group in Korea, I believe. They can identify plus vortices and minus vortices, and they can follow that as a function of time. So again, I think this, you know, they could form the pair distribution function and monitor it as a function of time. Once you have the distribution function, then you immediately get the energy spectrum. So I would... It's some polarization of the light going through that it shifts the polarization slightly for a vortex in one direction versus the other direction. I don't know the details. But actually, there's a more interesting case now. People have observed vortex pairs in ferromagnetic thin films. These are magnon condensed Bose condensate, superfluids. This is actually at 300 Kelvin. They use, again, some phase contrast methods to, you know, this is a micron spacing, but they can basically look at the phase of the spins and identify plus and minus vortices. And you can actually inject the vortices with electrodes of the proper polarity. So this is, I think, a very interesting system that you could possibly do experiments. It's two-dimensional, thin films, thin ferromagnetic films. Yeah. So let me conclude. I think this gives a very simple physical picture of the Enstrophy cascade. It's a picture you can't get from simulations, or is hard to get from simulations. I will make a wild claim that, in fact, this is the first analytic and fully renormalized theory of any type of vortex turbulence. Okay, I'm not aware of any analytic renormalized theories of any type of vortex cascade. And I think I've hopefully shown you that there's actually a fundamental connection between turbulent cascades and the phase ordering process of topological excitations. And I think that's again, it's an interesting insight that you get from the analytic solutions that you simply can't get from simulations. So thank you for your attention.